Welcome everyone to the 2020 edition of SEMLA, which is the Software Engineering for Machine Learning Applications Symposium. So this year edition, given our current international pandemic, SEMLA, instead of being an on-premise event at Polytechnic Montreal, will be a series of webinars. So we have prepared what I think is a very exciting program of webinars for these new editions. But before we dive into it, maybe let me briefly provide a bit of background of what is SEMLA. So SEMLA, it's actually a forum that aims to bring together leading experts in both software engineering and machine learning to reflect and discuss about the challenges of engineering software engineering systems that actually are built using machine learning. So the additional complexity that's bringing together machine learning system, AI-based system in the construction and the development and the release of software systems, it's the core goal of SEMLA. So we want the expert to reflect on this. So we hope through this series of webinars, you will get more insights about how to go about building these systems, what are the challenges of bringing them in productions, of maintaining them, and so on. So who are the SEMLA organizers? So SEMLA is organized by faculties at Polytechnic Montreal. So roughly we're 6 in the team. We have been pushing this. This is the 3rd edition. So we have Professor Adams, Professor Antonio, Professor Chang, Professor Foucault, myself, and Professor Naidi. So we all are faculty from Polytechnic Montreal, and we have been pushing this effort to provide a platform and a framework for the community to reflect on this critical and important issue that needs to be tackled if we want to bring this machine learning to grasp all the potentials that's its promise. So the program of this edition, it's composed of 6 webinars. So we are honored to have great speakers. We hope we'll really enjoy. So we have Diego, which is actually the CEO and founder of Algorithmia, providing the first keynotes today. Tomorrow, we will have Professor Katzner from Carnegie Mellon, touching on another aspect of building machine learning-based systems. Then we will have an interesting talk as well next Monday with Deng and Professor Vazi, touching about bias, which we know it's a very important aspect when you're building machine learning-based systems. Then on 23rd, we will have Grady, who I think everyone somehow in software engineering knows the work that's already have achieved, and he will provide us some reflection about how the AI component is impacting the process of building software systems. And we will have Professor Hamann, who will touch on a very interesting different aspect related to testing software systems that are built with AI-based component. So at this point, I will pass to Marius, who will be moderating today's talk, and he will be introducing our speaker. Marius, please.
Excellent. Thank you, Foots. So before we start, I have just one bit of information concerning logistics. So because we have, more than 200 attendees, thank you all very much for joining in today. We will be managing questions through the Q&A platform of Zoom. So you can type in your question in Zoom, and then we will relay the question to the speaker at the end of the talk. You can also see other people's questions. You can vote, so I'm going to choose the most popular ones. You can comment afterwards. Please include your name and your affiliation so that I can relay those with the question. The chat is also open, so you can discuss among yourselves, so we can have like a conference atmosphere, but any questions in the chat will not be relayed to the speaker, so please use the Q&A platform. So our first speaker for kicking off this SEMLA virtual symposium this year is Diego Oppenheimer, who is the founder and CEO of Algorithmia. He's an entrepreneur and product developer with an extensive background in all things about data. Before founding Algorithmia, he was at Microsoft working on some of the most popular data analysis products, including Excel, Power Pivot, SQL Server, and Power BI. Diego holds a bachelor's and master's degree from Carnegie Mellon University. A few words about Algorithmia. Algorithmia possibly one of the most representative companies for what SEMLA is, as it is an expert on DevOps for machine learning software. And they're working towards like fastest release, automated software development lifecycle, and secure delivery for AI and machine learning applications. So enough from my part. I would now pass it on to Diego to talk to us today on SEMLA.
Great. Thank you very much for the kind introduction. Very happy to be here. I am not a professor, but happy to be in front of so many professors here. So appreciate taking the time today to listen to me. So I'm going to share my screen real quick. Give me 1 second. Can somebody just tell me if my screen's showing?
It's visible. Yeah.
Perfect. Great.
Fine.
Great. So my talk today is going to be, we'll dive a little bit into technical stuff, but also a lot of kind of process. What I tried doing is really bringing to light a lot of our experience. So we've been working with some of the largest companies in the world in terms of how to develop software engineering, and more importantly, how to build machine learning into those processes. I'm a bit biased. One of the things that you'll see is I think all software will be powered in one way or another by machine learning in the future. And so from my perspective, the way I look at it is we're just seeing the early days of the future of software versus an entirely new world of machine learning being on its own. So I just consider this to be just the new kind of software that we'll be building. So let's get started on that. So thank you for the introduction. If you ever want to, get in contact with me, I'm very responsive on Twitter or either on LinkedIn. Feel free to reach out, and I'm happy to answer any questions around that. So I'm going to start kind of like with the journey of, what happens when we actually start building machine learning models. And one of the core actually things that, when I founded this company with my co-founder, so my co-founder, Kenny, was a PhD in machine learning. And he was essentially, he always kind of used to say this joke, which was, the future is already invented. It was but it's stuck inside an academic paper. And really the core of the way that we were thinking about that was there is so much innovation in the world of ML and new models coming out, but the consumption model and how applications can run those models, how organizations and businesses can take advantage of those models is still really early, and it's very problematic. And in a lot of cases, the people who have expertise in machine learning in terms of building models and training them and finding the data and cleansing the data and getting the right hyperparameters are not the people who understand how large-scale enterprise IT works and what the requirements are for actually being able to build out machine learning at scale inside an organization. And that mismatch is not just technological, but it's also kind of from a people function, right? Like in terms of how teams are organized, how people are organized. And so one of the things I want to take you through today and kind of like the journey here today is calling out some of the problems that we've seen in the industry. So as you are approaching these issues and as you're thinking about how you're going to scale out software engineering for machine learning, you can start thinking about some of these gaps that already exist in the industry and how you might be able to solve those. So the big question is, how do I deploy this model? And, the truth is that, grabbing a model and putting an API behind it and deploying a Flask app directly from a Jupyter notebook is not exactly complex. There's plenty of guides around that. But when you're actually thinking about how you're going to be using that model to run real world business cases, everything from real-time fraud analysis, things that really affect the business, the requirements and the needs become a lot more important. And that's what we'll be kind of discussing today. So if you remember anything from this talk, I won't quiz you at the end. There's no exam. But if you didn't remember anything, just remember this slide, which is machine learning is not the same as production machine learning. And when you're thinking about production machine learning, the types of problems and the kind of technical challenges that you need to face are very, very different. Things like cluster orchestration and distributed parallel processing, load balancing, model versioning, how GPUs are being utilized, how you're being a good neighbor to other things in the system, how you're actually updating containers and dependencies and APIs and version control and backup recovery. These are all things that become relevant in the world of production machine learning that are not typically covered when you're just thinking about train a model and kind of deploy it and just see if it works. And so, as I said, if you remember anything from today's talk, this is the only slide that matters, and the rest you will figure out on your own from there on. So I like to talk a little bit about what the definition of DevOps is. And so you kind of see where I'm going with this. So the definition of DevOps is a set of practices intended to reduce the time between committing a change to a system and the change being placed into normal production while ensuring high quality. So two things really to focus on: reducing time to production. Right? And there's a really big reason around this, and we'll talk kind of through that iteration process and philosophical process around why this matters. But at the end of the day, the one thing that you need to really understand is if a model is not in production, there's no value being achieved from that model by that organization. And again, I'm splitting out academic from kind of like real world business use cases, because in academia, you're doing the ultimate pursuit of truth. It's totally fine to just being like looking for better methodologies, looking for better accuracies, spending years working, kind of pursuing that ultimate truth. But in the world of business, it's really about affecting that business and how you actually get that. And so that's why getting into production is so important, because the entire workflow, everything from data prep to training to model building, only activates itself, and there's only a return on investment in all that effort if you achieve production. So these two things become really important, and the discipline of DevOps has solved this for software. And so we need to start thinking about, okay, well, what can we learn from the world of software and of traditional software development and apply that to machine learning? And it's not a one-to-one translation, because a lot of the parameters are very different. So just high level, to give you an idea from the industry. So we do run a survey every year. We have over 500 participants in the world of machine learning that take part of it. And what we've learned is that most machine learning engineers and data scientists are actually spending 75% plus of their time just dealing with infrastructure tasks. And this is interesting because usually, it's not that they're not capable, but these people are the ones who have the least experience in infrastructure tasks compared to other parts of an organization. More importantly, they're not spending the time really on the fact that, building better models, more accurate models, more performant models, so that they can actually, build that. And so when we start looking at what are the key challenges that those data scientists were supporting, we see that, supporting different languages and frameworks. It's really exciting to see the speed of iteration that the different frameworks are coming in. It feels like every 6 months, the industry has said that this is the next and best framework that we need to be all working with. So supporting that over time becomes a really expensive task. How do you manage models? How do you manage versions? How do you manage repeatability? How do you manage understanding what you called at what point with what data, and understanding how, that is, it becomes a pretty burdensome task in the world of software engineering with machine learning. And then how do you achieve scale? These are, in a lot of cases, extremely compute-intensive workloads, very expensive, that require a lot of coordination, and achieving scale has become quite a big of a problem in terms of if you have every single cell phone hitting a model in your organization, like that scale becomes quite daunting and important to address. So when we talk about, traditional software and we talk about the software development lifecycle, and in machine learning, we talk about the machine learning lifecycle. And my opinion is that these two will merge. we're not there yet. We're pretty early on in the journey, and this is just me being opinionated about it. But I think the future lies that these two things will actually merge into one. So what's really going to happen is that the traditional software development lifecycle will expand to be able to accept the parameters and conditions of machine learning. And I think that becomes, extremely important. So I'll talk a little bit about, today, walk you through that journey and kind of how that looks like. So when we look at traditional software dev cycle, right, we have source control, maybe using Git. We have continuous integration pipelines like Jenkins and GitLab. We have continuous deployment, which might be to different infrastructure providers like AWS, Heroku, Kubernetes. And then you have this management, which is how do you do monitoring? How do you do log aggregation? How do you actually work within the signals that the software is putting out so that you can understand behavior and guarantee performance using things like Elk and Grafana. So in the world of machine learning, we also can use Git, and we start looking at, hey, how can we actually use Git as our source control for our query code, for our inference code, for in some cases just traditionally versioning our notebooks and understanding the different code that we're using there. What are the tests? Continuous integration is what are the test sets that we want to verify against on every single run, making sure that we're actually represented accurately the data that we want to be working with. And from a continuous deployment, we have to start thinking about: do we need CPUs? Do we need GPUs? Do we need to deal with cold starts? In some cases, anybody who's worked with the latest and greatest NLP models, they're quite large. Loading the memory is not a trivial time. And so when you start thinking about performance, if you look at a website, for example, and you need to be returning an SLA of, under, 7 milliseconds in terms of, being able to response time on that, loading the model, a 500 megabyte model, a gigabyte model, that takes time. And so being able to actually understand where that time is going, how to prevent it, et cetera. And then from a management perspective, how do you do continuous evaluation? We have a unique condition inside the world of machine learning that data drifts. And, and it changes over time. And so our models are going to drift. And therefore, we need to be able to take advantage, understand that situation is happening and be able to build processes around that. So how is ML different, right? And so, first of all, it's a very, very new ecosystem. It's a ecosystem that is actually, evolving very quickly. And I usually joke around and I say, if we think about traditional software and operating systems, and we start with punch cards, and we go all the way to today, which is, iOS apps that are coming from a marketplace. In the world of machine learning, and the abstraction layers would be, punch cards, Unix systems, DOS, Windows, abstraction to mobile OSs. In the world of ML, we're closer to punch cards than we are to kind of like a fully abstracted mobile OSs. So very new ecosystem, an ecosystem that's evolving very quickly. Another condition of this is ML moves faster. And what I mean by that is that the iteration speed and the cycle is faster than any other software development that we've seen in history. The ability to test, deploy, run, verify, test, deploy, that iteration cycle, in many cases, when you look inside an organization, the data science team is the fastest moving team in terms of how much things they need to test and explore. And that's a very good thing, I think. But the traditional tools sometimes kind of break at that iteration speed. And then upgrades, traditional upgrades in ML is just often more data and changing the model, not actually changing any of the code behind it. And so what I'm showing here is that, we go through this training and iteration cycle in ML development, and then we actually have to go into our deployment life cycle, which is how do we manage that deployment? How do we connect the data services? How do we register pipelines into that? And finally into the operations aspect of things, which is, how do I know what's running, where it's running, how am I managing the infrastructure, and how am I doing monitoring, reporting? And this cycle is extremely iterative in that sense, and much faster than traditional DevOps. So I talk a little bit about Boyd's law of iteration. So whoever doesn't know about Boyd's law of iteration, Boyd was an ex-pilot, but also an engineer. And there's essentially like the story that he tells is, there's a MiG-15 and an F-86, I believe, and the F-86 was inferior to the MiG-15 in pretty much every single aspect. It was a slower airplane. It was it didn't have as much visibility. It didn't turn as well. But in dogfights, in traditional, the F-86 pilots won 9 out of 10 times. And the reason was because their actual pilot like node was actually a hydraulic stick versus a manual stick. And what it allowed them to do, the pilot, is the response time was so much quicker that it allowed them to iterate a lot faster in terms of what decisions the pilot needed to make. So they had an inferior structure in terms of the aircraft, but they had a much faster response time. And so Boyd's Law, which actually gets applied to software quite a bit, and especially into DevOps, is faster iteration almost is always better than higher quality iteration because it lets you go through the cycles a lot quicker. So building out your ML infrastructure for fast iteration, for being able to make decisions very quickly, for changing things very rapidly, is actually a huge advantage in the world of in the world of machine learning lifecycle. So I'll talk a little bit about a journey and, kind of how we think about architecting systems inside an organization. So obviously you have your data management systems. This is where you prepare your data, you prepare ETL pipelines, you have your feature stores, you understand how to clean your data and stuff like that. We traditionally then push that data or query that data from training systems. In large organizations, you will have multiple training systems. You will have multiple different frameworks. You will have multiple different tools around that. And then models and the algorithms to query those models get pushed into a deployment and operations platform. And that platform will actually build out a model portfolio, or do orchestration, dependency management, versioning, pipelining, and take care of kind of that governance and management of everything that's in production so that the apps can actually pull from that and use them actively in a governed way. So I'm not, there's a million talks about data. I'm not going to talk about data. Anybody on this call, I'm assuming, spends most of their time cleaning data or finding data. The fact is that data is useless without our algorithms, but algorithms are also useless without data. And so obviously this is an extremely important part, but it's not what I'm going to be focusing on today. I just do want to, kind of point out that this is an extremely important problem. I'm not just ignoring it. When we look at training, we have some pretty, interesting like architectural decisions from a compute perspective. So training and production are very different. And this is why trying to get one system that does both is extremely hard and actually destined to failure. If we think about how training runs go, these are usually long compute cycles, very interactive, very exploratory, stateful, and for the most part, single user application. So you usually maybe have a collaborative team, but like a training run is usually done by a single user in one way or another. But then when you actually move into production, this becomes quite different, right? Now we start thinking about models as extremely short but intense compute bursts, very elastic. In some cases, think about web traffic or think about credit card transactions, and many, many users. So it's a many-to-one paradigm in terms of how models get built, how models get productionized, and how they get run at scale. So how do we actually bridge the gap between training and production? So one of the things that we suggest to our customers is a 2-Git flow, which means that what we have is there's actually 2 distinct code bases, and that's on purpose, and we shouldn't try to merge them. You're going to have a training code base, which has its experiments. It's going to have all the data that's used, the versioning of the data, kind of how you actually are building that. And then you're going to have your inference, and that is actually the dependencies and things that are needed for running that model in a production workflow. And so one of the suggestions that we have to our organizations is you want to split these in 2, and you want to keep track of these 2 and have this kind of 2 repos across the board that you maintain, and then have some sort of automatic interaction between those 2 repos. This allows you to keep track and do reproducibility both at the inference side of things, but also at the training side of things. So when we're thinking about deployment, right, it should be easy to work with directly from the tools. And so if your preference is Jupyter Notebook, and your organization is using a Jupyter Notebook or using something like Streamlit or something like that, you want to be able to actually deploy models directly from that into a system that kind of takes care of a lot of these things. And so again, there's no reason why the data scientists, machine learning engineers can't have the tooling that they're using today and comfortable with, but you'll be actually interacting with two different models, two different systems, training systems, as well as the deployment and management systems. But when you're actually doing ML deployment, there's some really unique challenges. Not to mention, if we think about the use of GPUs. So GPUs in themselves, they don't have the guardrails that CPUs have at memory management. They don't have, it's getting better, but the fact is that really being able to get down to the drivers and understand the CUDA level, and these become all important for inference time, for SLAs that you need, and for consistency around the runs. And so actually you have a unique challenge now that when you're actually going to be running machine learning models in production, you have to deal with a whole new set of software that traditional software is just really around CPUs and stuff like that. So just to think about it, we talk about how we can containerize models, and that's a great way of getting to a certain level of reproducibility and portability. But a model, while we like to think about it, a Docker container is not a VM. Right? So if you think about how multiple containers inside a machine, it's not a VM where they'll have their own unique drivers, their own unique kernel, their own unique OS. In the world of Docker containers, there's shared kernels, there's shared memory, and security concerns show up from that. Making sure that you're a good citizen, actually having to change the drivers around can affect other machines. So these are all the things that you need to start thinking about when you're actually productionizing model, which is slightly different from just running in your own isolated environment. Think about kind of heterogeneous tooling. Most machine learning pipelines are quite heterogeneous. You will be working with, a TensorFlow model. You might have some R pre-processing functions. You might be deploying a Java, post-processing function. Being able to actually deal with how the different models use different frameworks, different versions of language, different CUDA, this all becomes really, really hard to manage. So you have to start thinking about when you're setting up yourself for success in kind of this DevOps aspect, how do we actually deal with dozens of languages and frameworks? How do we deal with hardware dependencies? How do we deal with new frameworks that are coming up and build a platform or at least a architecture that is going to allow for those that variety and heterogeneity? I talk about composability. Again, I don't know of a single real use case of machine learning where it's a single model living on its own. They are always pipelines being built in the real world. And so being able to actually quickly interact with those pipelines, being able to update the different components independently, being able to deal with the dependencies that those components have from languages and frameworks independently becomes super important. And then finally, how do you manage all of this? How do we understand that we're getting the right success from the models? How do we monitor that we're actually affecting the business or in the right way? There's not one model that's ever going to be the right job, the right for every job. So how do we actually test different models against each other and different use cases in a fast, iterative way? And again, one thing that you'll see here from everyone's slides, like iteration speed, is really the key of success in actually being able to scale out machine learning efforts. And finally, where are the tests? And I know that this is something that anybody in traditional software engineering is very comfortable with. What do we do about unit tests, integration tests, smoke tests, performance tests, stress tests? This is something that we understand really well. Well, are we applying these to machine learning? Are we actually verifying, performance around SLAs on every new model? What happens if I just trained a new model and I increase the accuracy, but now it takes, twice as long to do inference? Is that okay? Maybe, maybe not. We don't, this is the part that needs to be started to think about as we make a more sophisticated effort for a discipline around software engineering, is to start bringing these elements from traditional software into the world of machine learning and educating, in a lot of cases, the data science teams, the machine learning teams, why these are important and how to build these tests for their specific things. And then things like, which are very traditional to ML, which like model and concept drift, as well as A, B, C, D, E, F testing around different model versions. And then one thing that we kind of forget about in a lot of cases, but which is auditability and governance. If you are in financial services and you are making decisions around financial services, let's say loan applications, there is regulatory concerns around what decisions were made, and the regulators can ask why that happened and when it happened. And so being able to understand who called what model with what data at what time and what results were provided of that becomes extremely important for actually being able to use these systems in production. Same thing with life sciences. If you're doing drug discovery using machine learning and you want to get that drug approved in one way or other, that methodology needs to be able to package and given to a regulator who can actually go through it and say, okay, we see all the runs, we see all the verifications that were made. And so does your system allow for this kind of logging? Are you expecting this kind of logging to happen? And can you actually retrieve that data in a reasonable way to be able to package and send that out? And then security is the other one, which is how are you accessing the different dependencies? What dependencies are you bringing into your machine learning code? Are they secure? Are they compliant with your organization? So this becomes a lot of the kind of DevOps aspects and becomes super important when you're thinking about machine learning at scale. So obviously model drift and is becomes extremely important. So if I have a system that is doing fashion recognition and every single picture over the summer, these are all the pictures that have been coming in and my system's working pretty well, it's unlikely when the winter comes that model is going to work just as well when the clothing has changed entirely. So starting to think about how do you adapt to ever-changing data coming through the systems, and being able to build guardrails around that and adaptability around that becomes extremely important. So introspection is a big part of how do you manage, and should be part of the DevOps aspect of any machine learning workflow, which is how do you do logging, how do you do monitoring, how do you do alerting, how do you do observability around that. So in a lot of cases, deploying machine learning in production at organizations is really economically challenging. And the reason for this is there's a lack of process, there's the wrong incentives for the teams. Sometimes you have the wrong teams talking about it, you have the wrong technology, or you have the lack of proper champions. And so I'm going to talk a little bit about these kind of 5 missteps that exist and kind of how you might be able to address those. So how do we tackle a model stuck in the lab? How do we tackle disconnected teams? How do we plan for technological mismatch? How do you actually convince people to invest? And then how do we deal with the technical debt that exists in pretty much every single machine learning workflow that I've seen in my career? So stuck in the lab. So you're deciding to invest in data science as an organization, and you think AI is a competitive advantage. You've funded a proof of concept or an experiment. Models are being trained, and the concepts are actually being existing, but they're never deployed. And the reason why they're never deployed is because people are not going into the situation thinking how this is going to live in production. So one of the things that we recommend to all our customers is thinking, hey, if you're going to be using machine learning as part of your software development process, and you're going to be actually affecting a business in one way, start from how this gets deployed and work backwards. Like, do you have the right people? Do you have the right technology? Do you understand how this model is going to operate in production? Because if you don't understand that, what's going to happen is you're going to get all the way to the end of this journey, and then you're going to spend the next 9 to 18 months trying to get that model into production. And these times are actual from our survey. These are the actual times that we're hearing from the industry, which is it's taking them 9 to 18 months to actually be able to deploy that. So understanding how production works in my enterprise, who needs to be involved, and who funds production becomes extremely important. Disconnected teams. So, one of the things, and you probably, in this audience, this probably happened to you at one point or another. We're asking data scientists to build infrastructure. It's not that they're not capable. These are very smart people who understand software, but this is really not their area of expertise, and it's not really where they're trained or have their, have most of their experience in. And so with lack of DevOps experience inside these machine learning teams, a lot of mistakes get made, but also it's just not as fast to getting up and running. So when one of the big red flags that we point out is when we see a data science team or a machine learning team, an organization who has not created a relationship with their DevOps team to understand how DevOps works inside an organization, we say that that's a pretty big red flag, because you need to understand how production, how the systems work, how you're going to be integrating into those workflow. And again, to where I started my talk, which is I fully believe that the world of software, the software development lifecycle and the machine learning lifecycle are going to merge into each other, in the next couple of years. And so this is going to become even more important. So things that you need to answer: does my team have the right skill sets to make my solution deployable in the organization? And that's really it, right? Do we understand the path to production and why we actually need to do that? So who's responsible for all of this, right? And it's kind of funny, or we see that because we don't really think about, this is not a technological problem. This is a human problem. How do we organize ourselves inside, inside teams? You have the data scientists, you have DevOps, you have business executives. What happens when all of these, from a hierarchical perspective, don't really match up in an organization? Or, the person, it's the CEO who's the first point of, where these two merge. So, Conway's Law talks about how organizations which design systems are usually constrained to produce designs which are copies of their communication structures. And so when you have a data science team that's not talking to a DevOps team, that's not really talking to the business, you end up designing something that isolates any one of those. And you actually need business owners, DevOps, and data scientists and machine learning engineers to be on the same page for any of these projects to be successful. So this is one of those things that has nothing to do with technology, but it's really about organizations and how they approach these technology problems. So then we talk about technology mismatch. So in most organizations, machine learning is super early and data science is super early. So there's not a defined stack. There is not a defined best practices. Everything's being built ad hoc. There's no building for repeatability, measurability, auditability. In some cases, certain tools are being used that are, really like locking people into just one path of doing things. We're not thinking about how do we access data. And there's differences between prod and dev. And so how do we answer what is the best ML architecture for my organization? Because the reality is that larger the organization, the more tools are going to exist. If you think about traditional software development, right? A DevOps team usually says, okay, well, we need to be able to deal with people building stuff in any IDEs, building stuff in any languages. They've really abstracted the tooling from the processes of getting things into production. And we need the exact same thing in the world of machine learning. The tools are only growing and they're only going to be more and more of those. And that's a totally okay thing. We want to use the best tool for the best use case. And so then we start thinking about infrastructure. Where is this going to run? And a lot of organizations are thinking, well, I need on-premises, I need cloud, I need multiple clouds. So being able to abstract and not marry yourself to a specific infrastructure becomes important. Well, what are the deployment technologies? In some cases, that might be Kubernetes, it might be VMs. What are the different CI/CD processes inside my organization? There's multiple of them. And so when you're starting to think about how machine learning is going to achieve production, abstraction and repeatability across different types of tooling becomes that much more important. So then we talk about stakeholder buy-in. Again, this is another human problem, not as much as a technology problem, which is how do I actually get people to understand what I'm doing and champion that? So in a lot of cases with any new tech deployment, a lack of champions will actually be really detrimental. How do I actually find the right people who are going to get advantage of what I'm building? So if I'm actually doing a fraud model, how do I make sure that the people in risk at an organization are really bought into this because they understand how reducing fraud is going to be so much better for them and it's part of their task. And so a big part of the success behind ML projects is finding the right sponsorship, right? And just think about kind of like in the world of academia, finding the right PI for the kind of work that you want to do. It's just the same in the world of business. You have to find the right person and people who are going to champion the idea of what you're building, understand that it's an iterative process, understand that you can get small wins, but it's going to take a while, and champion all the process. Because otherwise, a lot of these ML projects will die because of skepticism or unfamiliarity, or understanding that in the first iteration it's just not going to be as good and that you need to actually increase that over time. So lack of process becomes really important as well. And this goes back to kind of like a technology as well as a human perspective, which is it's actually really easy to get proof of concepts funded and experiments running. So once the results are shown, what do we do there? So who's going to fund production? Who needs to be involved? How does production work in my enterprise? And so one of the key things that you need to be able to answer is, how do we go from POC to production? And really the solution is plan and fund deployment up front, set clear deployment criteria, bring in stakeholders from IT and DevOps early, and then always build for repeatability in the process. And these are things that you can start thinking about from day one, but even though our natural inclination is to say, oh, I'm just going to see if I can get better accuracy about this model, that's not, in the world of, you know, in the real world, again, outside of academia where you're pursuing, you know, the ultimate truth, you know, that's not the right place to start. And so one of the frameworks that I really like, I didn't create this framework. It's a gentleman in Canada actually called Ian Xiao. He writes a whole bunch about this, and I really like his how he thinks about this problem. And what he talks about is so you can go look at this in ML is Boring. I have a link at it at the end of my talk, but he talks about a minimal justifiable improvement tree. So if you think about in traditional software, we talk about an MVP, right? The minimal viable product. And so what he thinks is like, well, what's the minimal viable improvement that is worth doing a whole thing around, you know, a whole machine learning process? And so you start from the problem, right? So if I'm thinking about building a new machine learning model that is going to, you know, provide me with $1 million worth of savings a year, but we actually think that it's going to take, you know, 2 years to get there and $2 million, that's not a good pursuit. Right? And so starting to understand, hey, what do we think is the objective? Is this the right problem? What are the right constraints? Is the savings or optimization that I'm going to get from my ML process going to be good enough? And then start working your way down to what's the business process that we're optimizing? What kind of technology we're going to be using? Is it in the right organization? And can we afford it in some way? And then is just when you start with technology. We as engineers have a tendency to work bottoms up in this tree, where we want to start with technology and then hope that we can adapt it to the business. And that is not a winning proposal. What we really want to do is start with the objective and work our way down. So I really like this framework of minimal justifiable improvement tree. And as I said, it's not mine. Ian invented it. So I highly recommend you go do some of his reading on that. So what's happening, right? So ML is in a huge growth phase, but it's difficult and expensive for DevOps to keep up. So a few models and a couple of frameworks, 1 or 2 languages is not a problem. You know, when we have dedicated hardware or VM hosting, it's not a problem. But once we start actually thinking about, you know, how do we get to true heterogeneous APIs, thousands of algorithms that can and models that can go from 1 to 1,000, TPS variants. You know, we need to start thinking about auto deployment, discoverability, low latency, common API patterns, composability, and fine-grained security. And these are all things that the world of DevOps has solved to a certain degree for software development, and we can borrow in the world of ML and start bringing to the practice so that we can actually ensure the success of what we're doing. One of the things that I talk about, like, I don't think we're going to be seeing any sort of new AI winter anytime soon, but the complexity and the repeatability and the scalability that needs to be achieved, there's a lot of work that needs to be done in the world of ML to be able to actually even deal with the task that we're being asked to solve for, which is high repeatability, high speed of getting models into production and affecting businesses around the globe. So then finally, it's the hidden technical debt, which is, it's really difficult and expensive for DevOps to keep up with the rate of machine learning. So, it's easy when there's a little bit of, there's not a lot of these systems, but as soon as you start growing, and there's a great paper by Google, the hidden technical debt in machine learning systems. So we have to start thinking about the best way to do machine learning operations and management at scale. And this is actually the problem to solve, for true success of ML to become, ubiquitous in the world of software development. So some of the considerations for those of you who might be working in enterprises for ML: how do I do infrastructure agnostic deployments? How do I actually provide collaboration and pipelining? What are the performance SLAs? How do I measure those performance SLAs? And then how do I meet them or mitigate if I don't? What's the kind of regulatory compliance that I need to be building into my system? What kind of governance is needed for this, for this kind of workflow? How do I do accounting and what's called chargeback tracking, which is if I'm running a large ML system that's very expensive on infrastructure and multiple teams are using that, how do I charge them? How do I share the cost of that infrastructure, which is very needed? And those are built into traditional software systems. And then how do I do security and authentication? So these are all the things you need to start worrying about when you're actually looking at making kind of like that DevOps journey for machine learning. And then navigate some of the common pitfalls. We're technologists. We love tinkering. We love working with new technology, but reinventing the wheel is really counterproductive. Focus on outcomes, not the actual process of getting there. Don't try to be perfect. Again, iteration speed is more important than accuracy in almost every single use case. And so, because you'll get to the same result. Say no to lock-in in terms of tooling. Think flexibility and integrations over time. Tools are not solutions to these workflows. You have to think about the human as well as the technology aspect of it, and then audit honestly and revise constantly. So just because you solved something in a good way, 2 months ago, does not mean that that's the best way of solving it tomorrow. And so being honest about, hey, what parts of the system need to be upgraded around that becomes super important. So as I said, and I want to leave some time for questions, if you remember one thing from my talk, I hope you take this away, which is machine learning is not production machine learning. We spent the last 2 decades learning best practices in software engineering. We can actually take those lessons and apply them to the world of machine learning. And it's not just about the ML, right? It's all the components that exist around that and picking the right tools for the job in that world. Thank you very much for listening, and I'll happily take any questions right now. I think Mario is looking at it as we speak. But thank you very much for your time today.
Thank you very much, Diego. That was amazing. I hope everybody enjoyed it as much as I did. I will resist, and I will not take the privilege of the microphone, and I will not ask my personal questions now. We have a lot of questions, I think. The talk created quite a bit of buzz. So I will start with the most popular, let's say, questions, and then I will go on to one from the beginning. So the first one is kind of philosophical. Juan Pablo Sugaca David asks, according to you, which would be the main difference between a data scientist and a machine learning engineer?
Right. So a data scientist is going to be a lot more focused on the finding the data, cleaning the data, setting up the data, building the model. In most cases, the ML. So first of all, these two roles get mixed a lot. The ML engineer tends to be the one focusing on how this is going to work at scale and how the system is going to run. So in a lot of cases, again, different enterprises do different things, but we see the data scientist building a model, and they might actually just end up with a notebook and saying, here's some R code that shows that we can do this. And the ML engineer might be the one translating that into a more robust system. In the worst case, in my opinion, is when you have to rewrite that entire thing. So a good example of this in financial services is it all starts in MATLAB and then it ends up in C++. And so there's a translation there, and an ML engineer might be focused on that. In a lot of cases, the ML engineer is the one hooking up the different data pipelines and the different data systems and focusing on how this is going to be run at scale or for that use case versus just doing the exploratory get to the model working in the first place. So that's kind of what I've seen as the split. I think these two terms get mixed a lot, and especially and so it's hard to make a strong line between the two.
Mm-hmm. I agree. Well, thank you very much. So we're moving on to the second question from Marcus Borg from the RISE Research Institute of Sweden. Marcus asks more of an entrepreneurial question, I guess. So suppose an organization wants to build its first infrastructure to turn some cool classification model into production tomorrow. Where should they start? Which solution would you point them at? If there are any particular recommended tool chains?
So I would say, first I would start again from, I would always pick iteration speed. What's the fastest way to get something up and running? Because the chances are is that the first thing you get running is wrong or won't work. And so getting to, I kind of I think of it as a kind of almost like evolutional theory, right? Where we want the strong systems to survive and the weak systems to die, but we want them to die quickly so we don't spend too much time on them. And so from a stack perspective, I would look at where's your data, what do you need to do with that data, and what are the tools that you can just offset so you don't have to build. So build the least amount of things possible. Use as much of the stuff that's off the shelf as possible to get you to the first iteration. Once you get to that first iteration, you're going to learn a lot about what is working, what's not going to work, what's going to break. And if it's modularized, your stack is modularized. This is why betting entirely on one stack becomes really complex. You can start replacing those things and advancing them. So again, I'd be hyper focused on getting something out the door as quickly as possible so that you can take advantage of that learning and then go backwards and start optimizing your stack.
Excellent. Thank you. So I personally find the next question quite interesting. It's from Benjamin Benny from Concordia University. Can you quantify the scale of what you would call fast in the machine learning lifecycle? Are we talking about hours, minutes?
Sure. So again, it depends, right? And so in some cases, we want models being retrained and deployed every minute, potentially. I mean, that's kind of like the extreme, I would argue. But if you think about systems that would be, let's think about a trading system, right? Where, you're reacting to millisecond movements in markets. And you want, you might have a situation where you need models being learning and redeployed instantly over and over again to take advantage of those arbitrage opportunities. I would say that's an extreme on one side. I think what we see a lot of is daily retraining and deploying. A lot of recommender systems tend to kind of look at all the new data on a batch overnight and then redeploy themselves on a daily basis. We have multiple customers, for example, in the network security aspect of things where, they're retraining and deploying a new model every hour and testing, it's like it takes about 15 minutes to retrain. It gets deployed. There's a 5 minutes of verification. And then, that model either is better or worse. And if that model is better based on the signals, they adopt it. And so it really varies. I would argue, as I said, I think the every minute is probably a complete extreme in corner case. But we've seen quite a bit of, at least daily retrained models and deployed. And so if you think about, if it takes me, 9 months to deploy a model and I'm supposed to be retraining it every night and redeploying, that's a problem. So I think that's the focus. If you go use, I have to give the little pitch. If you go use Algorithmia, which anybody can go sign up for free and test it out, a model redeployed, takes about 30 seconds at most. And so, you can automate that into your CI/CD process.
Mm-hmm. Excellent. Thank you. So the next question is from Pierre Langlois from Polytechnique Montreal. Pierre asks, what are your thoughts on implementation targets other than CPUs or GPUs and so on? How about FPGA-enabled servers?
Right. So I'm going to be honest, I don't have a ton of experience because we focus a lot on what's in production at organizations today, so businesses, and there's not that much in the world of FPGAs today. we're seeing some, definitely trends into that. I think from a infrastructure and a planning and DevOps perspective, it's just another target architecture. So understanding that it might be there and it has to be taken care of becomes important. But it's just not an area of expertise that I have. So while I've spent most of the last 5 years dealing with GPUs, ASICs are just not something I have a ton of experience with, or FPGAs around that. But we start seeing those at the inference side, right? Which is kind of where I look at production as just another target architecture that needs to be dealt with. And when you start abstracting and just assume you're going to have multiple different hardware targets, you kind of can plan for each one of those hardware targets based on the conditions that they have and kind of how those get packaged, while your system just needs to understand it needs to deal with that. So I don't have a super deep answer, sorry.
Thank you very much. So there is another question that is quite repeated. So Jerry Howard, as well as Manish Shankar Mondal from University of Saskatchewan asked, how do you define, and if you can elaborate on what infrastructure tasks are?
So infrastructure tasks are going to be different on training and on inference side of things. So if you think about on training, it resembles a lot more the world of high performance computing, in the sense of that you're probably going to have to reserve in the cloud you can just take over it, but you reserve large amounts of hardware, coordinate GPUs or CPUs, potentially do distributed training. So the infrastructure tasks are around setting up the training run, so building out the infrastructure, coordinating how to distribute the workload between that infrastructure, capturing the results of the runs as they go. So kind of like that stateful, kind of save, checkpointing, stuff like that. And then reducing those results to a target data store, and then taking down that infrastructure. So all of that orchestration, connecting to the data sources, being able to pull it, authentication will become relevant there. When you look at inference, it's slightly different in the sense that you're probably not going to have a fixed capacity load. So you're not going to know what the load is in a lot of cases, because it'll be dependent on certain traffic. Each one of the runs or models are technically, they're, as I said, one to many. So they're stateless in the sense that my inference and your inference are kind of irrelevant. So the scale out, the horizontal scale out, coordinating that horizontal scale out, coordinating for multiple user pools, coordinating for authentication, being able to dynamically scale up and down, and then again, connect to data sources and stuff like that. So those are kind of how the two infrastructure orchestration systems vary. They're quite different architecturally, even though they're both orchestration.
Mm-hmm. Great, thank you. So I'll try to, I will attempt to do something possibly a bit dangerous, but I have two questions that are quite similar, although they may take different angles. So Professor Ahmed Hassan from the SAY lab at Queen's University asks, can you talk briefly about version and release management in an ML context? How do you do versioning of data and linking it to ML code? And Benjamin Benny, again from Concordia University, adds, okay, I can understand versioning and differencing of code. What I would see between two, what differences do I expect to see between two versions of a machine learning model?
Right. So I think, so if we think about, so data versioning, there's a bunch of tools that are coming out right now, which kind of capture in time the state of data. So there's some open source tools out there that are really focusing on how data gets transformed over time and kind of almost and providing version control for those data sets as they vary over time. So that's one way of thinking about the inputs into these systems. You have obviously the inference code that can just be, traditionally, Git repos and version around that. And then when you think about the models, there's a couple of different ways of doing it. If you're thinking about kind of the separation between the model file and the weights file, each one of those can be versioned independently. In some cases, if they're binaries, you can version binaries. You won't understand what the differences are inside them, but at least you have a reference point of, hey, this binary was run with this data set. And so then becomes the metadata linking becomes really important. So when you think about architecting the system at scale, what you want to understand is, where did the data come from? How did I train? What set did I train with? What the parameters I used? What the results of that was? And then when I'm running that model in production, what version of that specific model is it? What version of the query code I was using it? And then as I'm seeing the kind of inference results, I can see, okay, for these inputs, these were the results. That's the full story of management. And it's not one system. You really are hooking up, I have a random idea for I think there's a need for a product, which is a metadata layer across all these pieces that they, that people kind of like register into, because tracking it across the systems is what's really important. So you can actually provide a full history of any individual model and kind of its provenance around that. So specifically to the question, binaries, you can have hashes in blob storages is a good way of doing it if you want an actual implementation, and keeping track of, hey, this is the, you can sign binaries and keep track of models there, then relate that to the code and the different weights that are associated with that.
Excellent. So I think we can, I don't know how you feel, Diego. Do you feel that you can take a couple more questions? I think people are very.
We have many interesting questions on the.
Yeah, I can do 15 more minutes and then I'll have to run sadly.
Okay. Let's do a couple more. So Jeremy Bradbury from Ontario Institute of Technology asks, a lot of the opportunities discussed for DevOps in production ML are focused on scalability, performance, and so on. Are there opportunities for DevOps and software engineering to address challenges with bias, understandability, and trust in machine learning?
So I think, so in a lot of cases, so I think of it as the traditional compliance world, so if we think about kind of like ethics and compliance in large organizations, those are kind of human reviewed processes that can be technologically enhanced. And so in the world of DevOps, I would argue that when you're building your workflows, you want to insert, it's not just a technology problem. You want to insert checkpoints. So I'll give you a perfect example of this. Let's think about a lending model. And a lending model is highly regulated in terms of, if you're using, what data you're using, but more importantly, what features you're allowed to kind of, use, because the data might come up with something quite racist in terms of, from a human perspective, in terms of giving a loan or not. And so the human review process can be injected into the DevOps process in terms of how are we checking against bias? How are we checking against kind of general ethics? And should we be using these parameters in one way or another to make decisions? So the answer is yes, but it's not a technology thing. I don't think we're going to get to a world where we just get a bias plugin and we inject it on top of, we connect that to Jenkins and we're good to go, right? There's going to be it's a human aspect of understanding what the machine is doing, what parameters are being used, and how they're affecting decision making. And that can be part of the DevOps process from a workflow. So hopefully that answers the question. I don't generally believe that we're going to just get, as I said, a bias plugin that we can just install.
Mm-hmm. Excellent. So switching more to, let's say, an education question. Professor Merlo from Polytechnique Montreal asks how to convince or educate stakeholders about the benefits of production machine learning. Some often think that machine learning is something that can be done over summer by a student intern, for example.
Okay. Can you repeat that one more time for me?
So the question is how to convince or educate stakeholders, in many cases industrial stakeholders, about the benefits of production machine learning.
Sure.
To convince them that there are challenges, that's something that they should adopt, and it's not something that it can be easily done so that they can dismiss it.
Sure. So I think this was where it becomes really important to partner with the DevOps organizations inside enterprises, right? Because they actually understand, they might not understand anything about machine learning, but they understand about the challenges of driving any technology to production, right? And they will ask the right questions in terms of, have you thought about backups? And so once you have partnership with there, it's actually a lot easier to build a case of, well, again, we have to start going back to the kind of like minimal justifiable improvement. At the end of the day, the business leaders, only care about how this is going to affect the business, right? And it's not going to affect the business in any way unless it's in production. So that's kind of like a truth. And then you can actually work with, the DAO and say, okay, well, to achieve production, X, Y, Z needs to happen. And you can actually build, from there. And so that's kind of that's how we approach it and how we educate it. A lot of cases, again, we publish a lot of white papers on this. So I encourage you to go, check out. It's a little self-serving, so I apologize for that. But we do actually, publish a lot of white papers on these challenges and how to approach them and how to approach, roadmap to machine learning maturity. And that gives good arguments in terms of how you can actually talk to those leaders. But it's essentially just focusing on, if you want to get results from this, you're going to have to do this, right? And being able to tell that story becomes really important.
Excellent. So I'll try to not go too much over the questions. I have two more, I hope final ones that are quite interesting. The first one is kind of technical and relates back to the question about data versioning and model versioning. Professor Jack Jiang from York University here in Canada asks if you have any suggestions on how to do version control on machine learning, code, data, and models. And I would also add, is Git enough to do this?
So, again, I'm going to give you a biased answer because this is what our platform does. And so this is literally what Algorithmia does. We use Git, a combination of Git and blob storage to do. So we don't do data versioning because we think that that's kind of outside of our system because we don't do training. We've implemented it as a combination of Git and kind of blob storage hashing. And that's how in the combination of those two is how we've kept kind of like version control and management. And then the layer in production that really matters is API versioning as well, right? So the API signature, the inputs and outputs, that's kind of like the outside, it's kind of like even more to the right of that thing. So, I do believe that Git works really well for this. And we've had good success. Here's one of the things that we found why I think it's really important, especially in an enterprise environment. If you think about a model, let's just say you have a framework, let's say you're using TensorFlow and you're doing it in Python and you're bringing in a whole bunch of things in requirements.txt, right? So you're bringing in a whole bunch of dependencies. In most cases in data science world, like those dependencies are not being scanned for security, compliance, checks, and they're completely outside of the software development world. But if we actually start moving that code into like something like GitHub Enterprise, a lot of these organizations have automation around making sure that they're checking for all the dependencies. They're checking for security holds. They're checking for CVEs, and wrong and right versions. And so what you're allowing yourself to do by using something like, I think, Git, GitHub, GitLab, whatever you're using from that perspective, is that you're actually allowing now your code to participate in all this compliance and security that already exists in an organization. You don't have to rebuild it. And so that's why we think there's quite a big of an advantage. Now, it doesn't fit everything. As I said, you have to kind of version these things differently. But that's one way of, doing that we found a lot of success and your organizations are happy with.
And I would also like to add a small detail because I am working with health professionals. Data is a very sensitive matter. So uploading data in any kind of platform, they will never be convinced. No matter how much security and privacy you promise, they will never be convinced. And it's a very sensitive topic.
Yeah, and we actually, if you go to the Algorithmia blog, we've actually written about model security and some things that need to be thought about. So I didn't really cover that here. Security is kind of its entire own thing, but actually making sure that each inference and kind of pipeline is completely secured and locked out from the world. How the data get transported, who can access it, where that memory is being shared. These are all things that a DevOps security team would actually be very focused on, which we as data analysts and data scientists and data engineers rarely think about. I mean, we do when they tell us to think about it, but it's not our natural reaction to go think about it.
Yeah, I see. Okay, so moving on to the very final question, because we're already over time. Ishaya Gambo asks, how does requirements engineering fit within the scope of DevOps for ML?
How does requirements engineering fit in the scope of DevOps for ML? So, I think it's really about the way that I think about it is the journey of where this needs to land. So, as you're doing, you're building the requirements again, like how we have to answer that question. How is this going to run? Right? How is the final application? How is the business application, whatever that is, going to run this and integrate it? Because at the end of the day, that's the only thing that matters, right? Otherwise, it's a science project. It only becomes a real, ML, like when it actually starts running against the system. So that just figuring out how that's going to work. You have to go into an organization and say, okay, well, how does this iOS app get deployed and run, and how do we maintain it, and what are the update cycles? So that's kind of where the requirements engineering kind of has to come in, which is you have to understand that so that your kind of ML workflows can tie into that. And it's just about the destination, right? Because again, we're focused about production machine learning. It's really about how we're going to actually deliver. If I want to completely oversimplify the world of ML, right? What we're doing is we're building optimizations for, we're just building optimizations for processes, right? Using machines at scale. And so, well, how do we connect into those processes? How do we actually optimize those processes? We have to start from that question. How do we actually hook into them and then work the technology backwards? So that's kind of where I see it from a requirement, because at the end of the day, as I said, I'm completely oversimplifying the world of ML. Yeah. But if I just think about it as we're optimizing processes in one way or another, using machines, like that's kind of like we have to think about the destination first, and then build the journey there.
Excellent. So I apologize to the people whose questions were not answered. Thankfully, Diego has provided contact information. So if you have more, you can send them, or we can relay some questions to Diego. Diego, on behalf of the organization team for SEMLA 2020, would like to thank you very much for your time and for participating. That was a super interesting talk. I think I saw at some point we had about 290 participants. So I think that's an amazing number for a virtual SEMLA. Thank you again for participating. I will pass it now to Foots to close this first day and talk to us about what's next for SEMLA.
Thank you, Marius, and thank you, Diego, for this very inspiring talks. I have very much enjoyed, and I hope everyone connected enjoy as much as I did. And thank you all for the interesting question that came in. So it's unfortunate that we couldn't answer all of them, but I hope the ones we picked provides a bit of broader context or a better understanding of these very interesting issues. So SEMLA is not over, it's just starting. So tomorrow we have another interesting talk coming, which will be by Professor Kastner from Carnegie Mellon. So if you haven't registered yet for this talk, it's still possible. So you still have time to register. And some of the questions related to requirement engineering that we touched at the end of Diego's talk, I bet will appear in tomorrow's talk. So you're very much welcome to join us tomorrow. And thank you all. Thank you very much for joining us. And I hope you have very, very much enjoyable upcoming weeks of talks. So we plan to have 2 talks per week for a total of 6 talks. Thank you very much.
Thank you so much.
Thank you all.